Today we're going to learn about average atomic masses and how to calculate them and the percentages. Protons determine the type of element, not the neutrons or electrons. In fact, for a given element, the number of neutrons can be different. We call those isotopes. These are the same element, but they have a different number of neutrons. And because they have a different number of neutrons, they have a different mass. Isotopes are actually named for their element and their mass. For example, carbon-14 has 6 protons because it's carbon. The 14 means that its mass is 14, which also means that it has 8 neutrons, because 6 protons plus 8 neutrons gives us 14 atomic mass units. The number of electrons, neutrons, and protons are figured the same for all regular elements, and we can see here that we have 3 examples: hydrogen, carbon, and oxygen, where we have, sticking with carbon, we have carbon-12, carbon-13, and carbon-14 as the common isotopes. If carbon-12 has a mass of 12 because we have 6 protons and 6 neutrons. Carbon-13, 6 protons and 7 neutrons, and carbon-14, as before, 6 protons and 8 neutrons. Hydrogen has 3 isotopes: protium, deuterium, and tritium. Protium means that it only has 1 proton. Deuterium, meaning 2, means that it has a mass of 2, 1 proton and 1 neutron. And tritium, or tri, meaning 3, has 1 proton and 2 neutrons for a mass of 3. So just to look at some common isotopes there. Remember that protons and neutrons have a mass of 1 atomic mass unit each. Now the actual masses are slightly more than that, but we're going to consider them just to be 1. Electrons have such a small mass that we don't actually include them in calculations of the atomic mass because they're about 2,000 times smaller than that of a proton or neutron. The average atomic mass, we're going to look at a periodic table and notice that all of them, except for the radioactive elements, have an atomic mass of a decimal. Now, why is that? This is because the atomic weights are actually a weighted average of all the isotopes that exist for that element. And we're going to learn how to determine the percentage abundance for each isotope. And that comes up now. Because the isotopes of an element exist in various percentages, the averages are calculated differently than we would normally calculate averages. It's not just adding them up and dividing by however many we have. So the formula to calculate this is below. We actually have 2 formulas here. If we do not know the percentages, then we use this first equation. The average atomic weight is equal to 1 minus x times the mass of the first isotope plus x times the mass of the second isotope. The average atomic weight, if we want to just calculate that and we are given the percentages, then we use the second one, where we have the percentage of the first times its mass plus the percentage of the second times its mass, and so on. AAW stands for average atomic weight. X for this first equation represents the percent abundance of one isotope, and we need to make sure that that is in decimal form. For example, 50% is 0.50 and 34.6% would be 0.346. Mass number 1 is the mass of the first isotope, and mass number 2 is the mass of the second isotope, both in atomic mass units. So here's an example problem. So let's pretend that we discover a new element, austenitium. There are 2 varieties of isotopes, austenitium-24 and 26. Austenitium-24 occurs in 1/3 or 33% of the time, and austenitium-26 occurs in 2/3 or 67% of the time. What is the average atomic mass? So remember, this would be a weighted average. Please pause the video and try to work this out on your own. So let's go through this as an example. So from our work, we saw that Australium exists as 24 and 26. So if we have Australium 24 and Australium 26, we're going to set the percentage for Australium 24 as 33% or 0.33, and for 26, 0.67. From the work we saw before, the average atomic weight is equal to the percentage times the mass times the percentage of the second one times the mass. And so we can just fill in here. So we have the average atomic weight equals the percentage 0.33 times the mass 24 plus the percentage of the second isotope 0.67 times its mass 26. If we plug that into our calculators, the average atomic mass or average atomic weight comes out to be 25.33 atomic mass units. Let's try another example. We're going to use copper as the example here, and copper exists as isotopes 63 and 65. The relative abundance and atomic masses are 69.2% for a mass of 62.93 atomic mass units and 30.8% for a mass of 64.93 atomic mass units. Calculate the average atomic mass of copper. So here we find the information that was on that last PowerPoint slide. We have the mass of copper 63. That's 62.93 atomic mass units for a percentage of 69.2. And 65 has a mass of 64.93 and an abundance of 30.8. So we can put that into our equation with the percentages as decimals, 0.692 times the mass, 62.93, plus the percentage, 0.308, times its mass, 64.93. We plug this into a calculator, and we get the number 63.54 atomic mass units. Hopefully you have the same value. And if you look at the periodic table, you will see that that, in fact, is the same value that we find there. We're going to finish today with one more example. Now this is an example going the other way, where we can see here that we have the average atomic mass already, and we have the two isotopes here. So now it's asking us to determine the relative abundance of each isotope. Now we're going to use the formula that we found earlier here. So I'm going to ask you to pause this video and work out this problem, and then push play to have the answers revealed to you. Now that you've worked through the problem, we're going to go through this one step at a time. So we have 56.84 was the atomic weight, equals 1 minus x times 55, the mass of the first isotope, plus x times 57, the mass of the second isotope. Using the distributive property, We then combine the x's, negative 55x and positive 57x, to get positive 2x. We then subtract 55 from both sides of the equation to get 1.84 equals 2x. We then divide both sides by 2 to get 0.92 equals x. Now what that means is that x is 0.92, or 92%. And the rest, 1 minus x, would be 0.08, or 8% abundance. That means that 2-Higium-57 is 92%, and 2-Higium-55 has 8%. Make sure you take notes on this video, rewind it, pause it as needed. If you need to watch it again, do that. But you are responsible for your own learning in this, and there may even be a pop quiz. So, good luck.